Consider the case when I toss a ball up. As soon as it leaves my hand, ignoring air resistance and the minute differences in gravity, the ball follows a parabolic trajectory. The study of such trajectories is called ballistics, and assuming I know the exact velocity at which it leaves my hand, I can compute how high it travels and how long it's going to take until it comes back down and I can catch it. So here's the question. If I toss a ball up and down and measure that time, and then I drop a ball and let it drop for the exact same amount of time, which one travels farther? Is it the ball that I toss, since it's going up and down, or is it the ball that I drop, since it only has one direction to go and it's going to keep going faster as it falls? Well, let's take a look at the math. Since I'm only considering the path of the object in the vertical dimension, I'll look at the equations with just one position coordinate rather than 2 or 3 if we were considering full three-dimensional space. First, we'll start the acceleration of the object, which we'll term as a, which under gravity is going to be approximately minus 9.8 meters per second squared, or minus 32.2 feet per second squared. Note that these are negative values, which we'll be interpreting as in the down direction, so positive will be in the up direction. So first, given acceleration, we'll find the object's velocity by integrating with respect to time. So we have the integral of just a with respect to time, which is going to be at plus some constant, which we'll call v naught for the initial velocity. For the thrown case, the initial velocity is going to be precisely how fast I throw it. But for the dropped case, the initial velocity will be 0 since it is starting from standstill. So clearly the balls are going to change speed at the same rate, and they're only going to differ at the initial speed. To get the position of the ball, then we're going to integrate this one more time, again with respect to t, to get 1/2 a t squared plus v naught t plus the initial position, which we'll call x naught. Just to keep things simple, we're going to set x naught equal to 0 for both of these, and we'll just handle that when we actually look at the end result values. So now we have the position with respect to time of both the thrown and the dropped balls. For the thrown ball, it'll be 1/2 at squared plus v naught times t, and for the drop ball, just 1/2 at squared. So what we're interested in measuring, again, is the total distance that the ball has traveled. For the thrown ball, it will be the distance it travels up, plus the distance it travels down. And for the drop ball, just the distance it travels down. So the first thing we want to do is figure out how long the thrown ball actually travels in the air. To do that, we can look at this a couple of different ways. The first thing we'll look at is how long it takes to get to the top of its flight, or the apex of its throw. And to do that, we can solve for when the velocity of t is equal to 0, since it comes to a stop at that point. If we set at plus v naught equal to 0, then we can pretty easily solve that t is equal to minus v naught over a. Since a is negative, the negative signs will cancel out, and we'll get a positive value of time, which makes sense since the ball comes to a stop in midair after we have thrown it. Now we can compute how far it has traveled by computing the position at this time. So if we plug this time into the position, we get x at time minus v naught over a equals 1/2 a minus v naught over a squared plus v naught times minus v naught over a. We can simplify this. The square will cancel out the minus sign. This a will cancel one of these a's. We get v naught squared over 2a and minus v naught squared over a, or just minus v naught squared over 2a. And again, a is negative, that will cancel out the negative, so we get a positive position. Since this was the position at the apex, and we know that it travels the exact same distance back down when it's dropped, the total distance traveled, which we will call x sub t for total, is going to be twice that, or minus v naught squared over a. The next thing we need to figure out is how long it took to travel this total distance. We already have the time it took to travel to the apex. Now we just need to figure out how long it took to drop back down. We can do this by going back to the position equation and solving for this equal to 0. And we can find that we can factor a t out of both sides. We get 1/2 at plus v naught times t. And if t is greater than 0, clearly this is going to have to be equal to 0. So we can solve 1/2 at plus v naught equal to 0 and get that t equals minus 2 v naught over a. So again, we know that the total time that we're dealing with is minus 2 v naught over a, which we'll put under both because that is what we're interested in. One interesting thing to observe is this is twice the time it took to reach the apex, which makes sense because the ball takes as long as it does going up to fall back down. So now we know the total distance the thrown ball went, and we know the total time it took. What we're interested in is solving the total distance of the dropped ball. At this point we have everything we need to know, so we can just plug in the total time into the distance for the dropped ball. Of course, we'll get a negative number here, which we will take the positive value of and interpret that as the total distance. So we plug this in, 1/2 a times minus 2 v naught over a squared. Again, the minus will cancel out. This will be a over 2 times 4 v naught squared over a squared. 1a cancels, the 4 over 2 simplifies to 2, and we have 2 v naught squared over a. And again, this is a negative value because the ball is going down, so we'll just simply take the negative of that to get the actual positive value. And so what we see is we expect the dropped ball to travel exactly twice the distance that the thrown ball traveled. In the same amount of time that it took the thrown ball to travel up and down, the dropped ball should travel twice that distance. Since the dropped ball starts at 0 and the thrown ball starts at 0 once it hits its apex, it's interesting to think that in half the time the dropped ball will travel exactly half that distance, and then the remaining time it travels 3 times the distance to add up to a total of twice the distance traveled. So now that we've done the math, let's see if we can reproduce this experimentally. So I have a tape measure, and I'm going to set this up here and just sort of toss the ball right in front of this. I'm not going to get this, I'm not able to produce an exact velocity. We'll look at this in the editor and see exactly how long it took for me to toss it and how far it went. So I'm going to make a fairly small toss because I don't have a lot of room here in the framing. Alright, let's go look at this in the video editor. Alright, so that took exactly 0.45 seconds and it traveled a total of 20 inches, 10 inches up and 10 inches down. So, we can work out what our initial velocity was. First of all, we'd like to convert those 20 inches into feet or meters to have a consistent unit. And so doing that, we find that 20 inches is 50.8 centimeters or 0.508 meters. So based on this, we can find the initial velocity by solving for it. So if we have 0.508 equals minus v naught squared over a, recalling that a is minus 9.8 meters per second squared, then we have velocity is going to be the square root of 0.508 times the acceleration. Again, of course, taking the positive value of this and the principal square root, which will work out to be about 2.23 meters per second. But importantly, now we get to test whether the dropped ball in the exact same 0.45 seconds will travel 40 inches. Alright, so here we come to the moment of truth, and let's find out if this will fall 40 inches in 0.45 seconds. And sure enough, we find that it took 27 frames, or about 0.43 seconds, which is certainly going to be within the margin of error that I find acceptable for this sort of experiment. So that's pretty awesome. Our experiment matched the math. While this is certainly not the first time this kind of experiment has ever been conducted, it's definitely fun to see the math work out and agree with the experimental evidence. If you like this video and want to see more like it, please like and hit the subscribe button. Feel free to share it with anybody else you know who likes this kind of video, and leave a comment below with what else you might be interested in. Thanks, and see you next time.